That disappearing act has far-reaching environmental implications. Because, as our next great discovery revealed, all the Earth's biological systems and the communities of life that depend on them are connected. The Dust Bowl of the 1930s. After years of drought, the once fertile American Midwest became a wasteland. Without rain, farmers continued to plow and plant, hoping that the nutrients in the fields would somehow be replenished. But their efforts only made things worse. The topsoil turned to dust, and the wind took its vengeance. For British ecologist Arthur Tansley, the Dust Bowl was proof that scientists, and the public at large, were too narrow in their view of the physical and biological world. They did not understand the dynamics of the environment as a whole, a perspective that helped explain the cause and effect of events like the Dust Bowl. He advocated a new concept, what he called the ecosystem.
The word has a simplicity to it. It's understandable by the ordinary person. It can be applied effectively, but it also has a scientific significance in that it brings together ideas from a variety of sciences. And
to understand the impact of Tansley's idea, I paid a visit to ecologist Frank Golly at the State Botanical Garden in Athens, Georgia. Why was this a revolutionary shift in thinking?
At that time, ecological work was strongly involved with the description of nature. In the systems approach, you are actually going further, you're experimenting, you're looking for patterns that are persistent across a variety of locations and species, and then you're making statements about the way they perform that can be tested. This moves ecology into the same venue as physics and chemistry and molecular biology.
And so Tansley took that word system
and applied it to ecological studies. He tried to convey the idea that ecology is part of a hierarchy of physical systems from the universe at one extreme to the atom at the other.
So somewhere in the middle would be solar system?
Yes.
And then down below that would be
ecosystems. Yeah. Back here is something I want to show you. The quantity of silt that you see in the river right now is due to the erosion of the farmland that's upstream. This is a opportunity to see what we could say was an ecosystem defined physically, Bill, right here in front of us.
It has boundaries.
It has boundaries. It's formed through a manipulation of the flood cycle, the river.
So this is a floodplain.
That's right. It receives water from the Oconee River. Periodically we get enormous rainfall and the river floods and would then send water into this sort of a area. We might be standing chest deep in water during a flood. Presumably at one time it was a forest. We see the remnants of the trees. But because of flooding and the persistence of flooding, the trees' roots were unable to respire and the trees died. You can see if you look around yourself here how beautiful the recovering forest is in its shape. We've studied that in great detail using an ecosystem approach, so that now we're able to talk about how to rebuild ecological systems here in this region by manipulating the various species and the environment to speed up the process, to get the endpoints we want to emphasize, and to do it at lesser costs. And that's a very positive step because we can rebuild nature to meet certain human needs and so that it functions and maintains itself on its own under solar power.
Solar power, yeah.
Under solar power, which is driving all the cycles and everything else.
Our journey through the greatest discoveries in the history of biology has revealed an amazing diversity of life on Earth. And it's given us insight into how that life works, from the life cycle of the smallest cell to the systems that govern the physical environment of our entire planet. But if there's one insight that resonates above all others, it's this: the search for more discoveries about life is never ending. That journey goes on forever.